So this is the second part of Monday, August 31st lesson, or for B Day, September 1st. And so for this handout, what I would like for you guys to do is to plot the points from the table. Just in case you are wondering if you should connect them or not, the answer is no, do not connect them, because we are only graphing and sketching a scatter plot. So because of that, we will only use the specific values that are given to us, and those will be the only points that we graph. Okay? If you did connect them, please erase that and make it look like a scatter plot. So I'm going to pause the video, and then we'll come back to check the answer. Okay, so that was our answer, well, the picture of a graph, and then this is a rational function, and the representative parent function is going to be the rational function, which we know looks like that. However, for our particular problem, problem number 1, this is the example of a discrete function. And the parent function is, if it's not discrete, it will be what? You guys remember? Starts with a C. Continuous. Thank you. All right. It doesn't matter that one is discrete, one is continuous, because we're just talking about representations, right, of the parent function. All right, and then quickly, we have here the point 0, 0. We have 1, 2, 4, 4, 9, 6. Could you guys think about the equation? Think about it for a minute as I'm graphing it. You don't have to, it's just like an extra. It is the square root, that's right there. So that will be the parent function, square root. We know that one looks right, roughly. And then 25, sometimes they don't give us enough space, so we have to get creative. So for 25, we have the point. And again, we're not connecting it because we're only making scatter plots, going by the instructions. So yes, that is the square root. Anyone could tell me the equation? Marco? Well, for this, if we were considering the function, so I will say x, and then there's something else that we're doing to it. All right, I'll tell you guys. It's a 2. 2 times the square root of x. So let's try it. Let's see if it works. What is the square root of 1? 1. What is 1 times 2? 2. So it works, right? Let's check the next one. What's the square root of 4? 2. And what is 2 times 2? 4. So it works. Let's do one more. What's the square root of 9? 3. And what is 3 times 2? 6. So it works. Let's do this one. The square root of 16 is 4. And 4 times 2? 8. So it works, right? All right. You don't need to know that because we're not experts with those type of functions yet, but we will cover them later on. All right. So let's go ahead and I'm going to follow. Okay, we're going to go over problem 5 first. So we have the table values, we have the graph, and now we're going to go ahead and answer questions 10 through 15. So before I do that, if I go the next day, it's going to turn into half of 1. What's half of 1? 0.5. How about day 9? 0.25. How about day 10? For day 10, we will have 0.125 milligrams, okay? All right, so let's go ahead and answer those questions quickly. So just to check the independent, don't be packing. Oh, okay. Independent is the time in days. The dependent is the amount of the medicine in milligrams. For the domain, we have from 0 to infinity. I'll explain that more in detail for the video. But let's go ahead to answer question number 10. What point is used to represent the amount of medicine in Daphne's system on Wednesday? So now, if you notice, the problem starts, day 0 is a Wednesday, but so is day 7, a Wednesday. So any of those 2 points will work. 0, 128, or what was the 1 for 7? Is it 1? Okay, thank you. All right, what does the point 3, 16 represent in the problem situation? What do you think, Andrew?
It's been 3 days and she has 16 milligrams of medicine.
Okay, I like the way you said it. So it's been 3 days. So after 3 days, or you could say day 3, she has 16 milligrams still in her body, correct? Very good. So now number 12, use the table to determine the amount left on the 8th day. We already did that, right? We took half of 1, which was the amount left on day 7. And so for day 8, we got 0.5, so 0.5 milligrams. Okay, number 13. The amount of substance in the system is considered negligible if it falls to 0.125. On what day will that happen? And we already continue our table, right? So that will be, I believe, is day 10. So after 10 days, the amount will still be there. It's just not possible to be detected. Okay, now 14. What is the parent function that best describes the data? What do you guys think? More or less? Starts with an E. Exponential. Will we say exponential growth or decay?
Okay.
Okay. Not that they're the same function. It's just we're just going a little bit more in detail. Exponential decay. All right, so that's it, guys. You're free to go. Now we're going to go over problem number 3. And for problem number 3, we're going to create a table. So I'm going to ask that you do that on your own. And so here we will have the dependent and independent variables. We could say that the independent will be the time in months. So we start at time 0, time 1, time 2, 3, 4, 5, and so on until we get to, I would say 10. Okay. Now, we start at time 0. Let's read the problem. So Jason's grandfather deposited $4,275 into an account to pay for his college expenses. And he is allowed to withdraw $475 each month. So what will happen here is that we start at time 0 with $4,275. And so to find out what will be the next amount, you could subtract 475 and where's the mistake here with my graph? So we start that, and if we subtract 475, we will get the amount 3,800. And so if we keep going in that way, then I believe it will be after 9 months when he will run out of money. So just keep subtracting 475 because that was Jason is withdrawing each month. After you do that, you could plot the points for the graph. And we know that we started at time 0 with this amount. Then after 1 month, turn into that amount. After 2 months, and turn into that. But please check your numbers. You may use a calculator for this problem. Now, we end up with a graph. And now if you notice the x and y axis, or the horizontal and vertical axis, we have them labeled different. So for this one, we decided to go by one. So 1, 2, 3, 4, 5, 6, and so on. For the vertical axis, which is representing the amount of money left, we went by 475. Okay, and of course the parent function is the linear function. Now let's look at problem number 4. And for problem number 4, we have a basketball being thrown. The starting point, the starting height, was 6 feet. And so at time 0, if you notice, the horizontal axis is being labeled as time in seconds. And for that, I labeled it by tenths, or by 0.1, 0.2, 0.3, 0.4, and so on. For the height, I'm going by ones, and that will be 1. And the height, it's important to specify this in feet. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what I did was just analyze the problem. You can construct a table here. So at time 0, the height was 6 feet. After 0.1 seconds, the height was 6.8. After 0.2 seconds, the height was 7.36, and so on. So just use the rest of the information. These problems were actually solved in class by the students, not by me. And so if you continue with the table and you plot your points, it should look like something like that. Now, in this case, the students and we discussed that, and we decided that they needed to be connected because the height of the basketball can be calculated at any time. So we could consider, for instance, second 0.15 right here. And there will be a particular height of the basketball at that specific time. To the contrary of that problem, if we go back to problem number 3, we decided to not connect them because Jason was only allowed to withdraw $475 each month, once a month. So for that one, it didn't really change. The amount after the first and the second month was the same. We're not going to worry about what happened between 1.5 months because the amount did not change. So going back to problem number 4, the representative parent function is quadratic. It does look like a parabola, and I know that it is missing a little bit, like a little part of it here. It doesn't look like a parabola, exactly like a parabola, but we need to consider an independent variable, which is time in seconds. And so the domain of this problem will start at time 0. We cannot discuss negative time. So even though you might think that it's missing a little part here, it's okay. It can still be have the same parent function as any other quadratic function. I'm going to just explain here what happened with the domain and range. And so in this case, we decided to connect the points because the amount of medicine could be traced between any day. So we could say 1.5 days, or 4.5 days, or 7.5 days. Now, for this one, I went ahead and explained how this we're not going to limit ourselves with day 9 or day 10. For this functions, they keep going. They do not touch the horizontal axis, meaning that the amount will get smaller and smaller and smaller, but it will never be 0. We could keep taking halves like we did here, half of 128, half of 64, half of 8, half of 4, half of 2, half of 1, and we can keep doing that, and you will never get to 0. The number will keep getting smaller, but never be 0 and never be negative. So because of that, we decided to represent our domain, starting with day 0, including day 0, and the largest or the biggest number of days will just be infinity. Someone in class mentioned, what about the day you died? And so I thought that was a good answer as well. If we knew when we were going to die, of course. But since we don't know, we will just call it infinity. For the range, the amount of medicine left, like I said, it could get smaller and smaller. It will get closer to 0, but it will never be 0. So because of that, we use parentheses to imply that 0 is not included. And the largest amount of medicine, which was present at the beginning, was 128 milligrams, including 128 milligrams. And of course, if we read the graph from left to right, it is clearly that it's pretty clear that the graph is decreasing. Okay, and that is the end of the video.